In this question, we're asked to work out a double integral on a region defined by its bounds. It's a region bounded by the curves y equals x squared and y equals 4x. Whenever we do a question like this, it's always best to plot the two curves so we can see what region we're integrating over. So let's just sketch our curves. We've got the curves y equals x squared. The curve looks like that. And we've got the line y equals 4x is a straight line. I haven't done this very well, but anyway, this is roughly the idea. So we're integrating over the region bounded by these curves. So we're integrating over the shaded area. And in order to do this integration, we need to work out where these curves meet. So they obviously meet at 0 here, and when x is 4, 4x is 16, x squared is also 16. So they also meet at this point 4, 16. So it's also, let's label the curves. This is y equals x squared. It's also useful to, in examples like this, to sort of write them the other way around. So that means that x is the square root of y. Similarly, this curve here is y equals 4x, or x equals y over 4. And you'll see those sort of rearranged x equals forms can be useful when we're determining the limits of our integration. Because that really is the difficulty of this question. It's determining the limits of our integration by defining this region. The region can be defined in two ways, really. There's two options. So either we say, well, x in this region, well, x varies between 0 and 4. Or we can say that y varies between 0 and 16. Okay. So those are two options. If x varies between 0 and 4, then what does y vary between? Well, now y depends on x. When x is 0, for example, y can only be 0. That's the only bit that's relevant. Whereas when x is 2, then y can take a larger value of ranges when x is 2. So the point is that y actually values between the lower curve, well, that's x squared, and the upper curve, well, that's 4x. So the possible values of y depend on x, but it clearly varies between the lower curve, x squared, and the upper curve, 4x. Let's now do it the other way around. So now, if we say that y varies between 0 and 16, well, now what does x vary between? Well, now we're going to go, let's just change the color. Now we're sort of looking in the other orientation. So we're saying, you know, how does x value? Let's say this is, I don't know, y equals, let's say that's y is 6. Where does x vary between? Well, the lowest value x can take is the left-hand curve now, which is x is y over 4. And the highest value it can take is the right-hand curve, which is x equals root y. So that's the two ways we can define this region. And that means there's two possible ways to do this integration. It doesn't really matter which way around you do it, as long as you get the limits correct. In this example, I'll do it both ways round, just so we can see that you get the same answer. So let's look at the left-hand side first. So we're integrating, we're doing a double integral, and if you remember the question, it was x squared plus 3xy. And what we're going to do is we're going to have the limits that are constant, so 0 to 4, are going to go on the outside, and the limits that depend on the other variable will go on the inside. So our x squared to 4x limits we'll do on the inside. And that means that we're integrating, well, the inner limits were the y limits and the outer limits were the x limits. So this integration can be written in this form, dy as a dy dx integral. If we do it the other way around, then now, rather than a dy dx integral, it's going to be a dx dy integral. So we're going to remember the inner integral is the one we integrate first. So we're going to integrate with respect to x first. Well, x is between y over 4 and root y. I tried to try limits above. And y is between 0 and 16. So these are the possibilities for our integration. As I said, they both give the same answer. Let's just follow through the first one on the left-hand side. So remember, we just do the inner integration first, which is the integral with respect to y. So we can just fill in the outer terms. What happens when I integrate x squared plus 3xy with respect to y? Remember, if we're integrating with respect to y, we're going to treat x as a constant. So x squared just integrates to give x squared y. And 3xy gives 3xy squared over 2. And this is between x squared and 4x. Now, when we substitute those limits in, remember those limits are going to be substituted in place of y. So the first limit, the upper limit, x squared y becomes x squared times 4x. We replace y with 4x, so I get 4x cubed. And then the second, 3xy squared over 2 becomes 3x times 4x squared. We replace y with 4x squared over 2. We take away the lower limit, so we replace y with x squared. We get x squared times x squared is x to the 4th. And we're going to take away 3x. Now, rather than y squared, we replace y with x squared, so we get x squared squared over 2 dx. Okay, we can simplify this all a little bit, so let's just rewrite it. We get 4x cubed, 4x squared times 3x is 16, it's 48, x cubed over 2 is 24 x cubed. Then we have minus x to the 4th, and we have minus 3, x squared is x to the 4th, so we get 3x to the 5 over 2 dx. Okay, we can combine the x cubed terms. We get the integral of 0 of 28 x cubed minus x to the 4 minus 3x to the 5 over 2 dx. Now this is just a simple integration involving x. So we integrate as usual. 28 x cubed goes to 28 x to the 4 over 4 minus x to the 5 over 5 minus 3 x to the 6 over 6 times 2 is 12. Again, between 0 and 4. We can simplify this a bit. We get 7x to the 4 minus x to the 5 over 5 minus x to the 6 over 4 between 4 and 0. And now we just substitute in the upper and lower limits. The upper limit is 4, so we get 7 times 4 to the 4 minus 4 to the 5 over 5 minus 4 to the 6 over 4. And then that's the upper limit, and we take away the lower limit. Well, the lower limit is 0, so whenever we substitute that into any of these terms, we just get 0. Okay, so now we can just plug these numbers in our calculator. 7 times 4 to the 4 minus 4 to the 5 divided by 5 minus 4 to the 6 divided by 4. I just get 563.2, which is my final answer. Okay, as I said, we should have done this integration the other way around. We could have done a dx dy integration rather than a dy dx, which is what we filled in on the right hand side. So let's just try this out. Let's try the right hand side and see if we do indeed get that same answer. So on the right hand side, again, we do the inner integration first, which is integration with respect to x. So x squared integrates to x cubed over 3, and 3xy integrates to 3x x squared y over 2, because we're treating y as a constant. And then our limits are root y and y over 4, and we haven't filled in the dy yet. So now let's evaluate this inner expression for our limits. So we still have the 16 and 0 dy. Okay, x cubed over 3. Well, remember the inner integral was with respect to x, so we're replacing x by root y. So root y cubed is y to the 1.5. And then the second, we're going to replace x by root y. So we get 3 times root y squared, which is 3 times y times another y. So we get 3y squared over 2. Take away the lower limit, I get y to the 4th, y to the cube over 4 cubed times 3. 4 cubed times 3 is, what's that, 192, 64 times 3, yeah. And then we also have to take away 3x squared y. Well, we'll replace x by y over 4, so we get 3y over 4 squared y over 2. Okay, let's just simplify this a little bit. I get y to the 1.5 over 3 plus 3y squared over 2 minus y cubed over 192, and that last term is 3y to the 4th, 3y cubed over 4 squared 16 over 32. Okay, good. A little bit complicated algebra, but it comes out in the end. Now we have just an integral with respect to y, so we're going to do a normal integral with respect to y. Y to the 1.5 over 3 is y to the 2.5 over 7.5 plus 3y cubed. That cancels out, doesn't it? So it's y cubed over 2 minus y to the 4 over 192 times 4, that's 768, minus 3y to the 4 over 4 lots of 32 is 128 for our limits of 16 and 0. Okay, and now we just plug these numbers in. So we get 16 to the 2.5 over 7.5 plus 16 cubed over 2 minus 16 to the 4 over 768 minus 3 times 16 to the 4 over 128. That's the upper limit, and we have to take away the lower limit, which was just 0 when we substituted. And now this is just something we can plug into our calculator. 16 to the 2.5 divided by 7.5 plus 16 cubed divided by 2 minus 16 to the 4 divided by 768 minus 3 times 16 to the 4 over 128. And again, I have checked it, and we do again get 563.2, which corresponds with our other answer. So we're again quite happy that we're on the right lines. Obviously, you don't have to do it in an exam. You don't have to do this twice. You just choose one side or the other, whichever one you're happier with setting up the regions and limits for. But either will be fine in the end.